All right, welcome back. Today, we're going to crack open one of the most essential, most versatile little components in all of electronics. Seriously, it's this tiny chip, but it powers a huge part of our world. So let's just dive right in and deconstruct the operational amplifier.
So what is an operational amplifier? You'll hear it called an op-amp most of the time. And honestly, you can think of it as the absolute workhorse of analog electronics. I mean, at its core, it's a high-gain device that does something really clever. It takes two inputs, looks for the teeny tiny difference between them, and then bam, it amplifies just that difference into one single, much stronger output.
But here's the thing. When you see one on a circuit board, it's just a simple black box with a few pins sticking out. It really doesn't look like much, does it? So that's the big question we're tackling today. What's the magic going on inside? What's hiding in that black box that makes this little chip so incredibly powerful?
Okay, to figure this out, we're going to follow a signal on its journey, right through the heart of the op-amp. And we're starting at the very beginning. Our first stop, the input stage. Think of this as the gatekeeper. Now, this first stage has one very, very specific job: to amplify only the difference between those two inputs, nothing else. And the way it pulls this off is with its key feature, something called high input impedance. Now, don't let the term scare you. Impedance is basically just resistance to current. So, what does it mean to have a high input impedance? What's that do for us?
Well, the absolute best way to picture it is to think of a really discerning bouncer at some exclusive club. You know, the kind with the velvet rope and a very, very specific set of rules. So here are the bouncer's rules. Rule number 1, it carefully compares the two signals trying to get in. Rule 2, it only lets the difference between them through to be amplified. Now this is huge because any signal that's the same on both inputs, you know, like pesky electrical noise that gets everywhere, it gets completely rejected, thrown out. And finally, remember that high input impedance? That's rule number 3, don't mess with the source. It means the bouncer can do all its work without drawing any power from the original signal. It just listens quietly, it never interferes. Pretty smart, right?
Okay, so our small, clean, different signal has made it past the bouncer. It's in the club. Now it's time for the main event. We're heading into what I like to call the high-gain engine room. This is where a tiny signal becomes absolutely huge.
The whole purpose of this stage is simple, but it is incredibly powerful. Provide massive voltage gain. That's it. It's just a pure gain booster. This is where the bulk of the amplification happens. And when I say bulk, I mean it. We're talking amplification by a factor of hundreds of thousands, sometimes even more. So if our input stage was that quiet bouncer listening for a faint whisper, this stage is like a series of giant megaphones all lined up in a row. It takes that tiny little whisper of a signal and turns it into an absolute earth-shaking roar.
Okay, but all that amplification creates a new problem. There's a catch. The way the internal circuits work, they often push the signal's whole baseline DC level way up, far away from the 0-volt reference point we actually need for the output. So, how do we fix that?
We fix it with another clever little section inside the op-amp, the level shifter. And its one and only job is to grab that roaring signal, take a look at its DC level, and just shift it right back down. It recenters the whole thing perfectly around 0 volts, getting it all prepped and ready for the final stage. It's an absolutely crucial correction.
And that brings us to the final stop on our signal's wild ride. It's been checked at the door, amplified into a roar, and then perfectly recentered. Now it's finally time to deliver that signal to the outside world. And that's the job of the powerful output stage. Now get this, the whole philosophy here completely flips on its head from what we saw at the input. The goal now is all about providing current driving capability, power. And the key feature to make that happen is the exact opposite of what we had before, a low output impedance.
So if the input was a quiet listener, think of this output stage as a powerful forklift. Its job is to take that big, beefy signal and deliver it to what we call a heavy external load. You know, something that needs some real current, like a speaker or a bright LED, and it does it without even breaking a sweat. No struggling, no signal voltage drooping, just pure power delivery.
And this contrast right here, this is the elegant genius of the op-amp's design. You've got a high impedance input that listens really carefully without messing with the source, and then you have a low impedance output that delivers power effortlessly without any loss. It is literally the best of both worlds, all in one tiny package.
So now that we've seen all the individual pieces of the puzzle, let's just take a quick step back and appreciate how this all works together by recapping that entire journey.
Okay, let's run through it one more time. Step 1, the signal hits the input, where it gets compared and all the common noise is rejected. Step 2, it goes to the gain stage and gets massively amplified. Step 3, the level shift swoops in to recenter it perfectly around 0 volts. And finally, Step 4, the output stage gives it the muscle it needs to drive the external load. 4 distinct stages, all working together in one seamless, incredibly powerful process.
But of course, none of this incredible work happens for free, right? There's a secret ingredient powering the whole show, the power supply. Specifically, op-amps almost always use a dual supply. They have both a positive voltage and a negative voltage. And that's what gives them the energy to do all this work. And, crucially, lets the output signal swing both above and below 0.
So you might be thinking, okay, that's cool, but why does this intricate internal design even matter? Well, it matters because all those stages working together make the op-amp an astonishingly versatile toolkit. This internal structure is exactly what lets us use it for, well, just about everything. We can make filters, we can create oscillators, we can do simple amplification, and you can even get it to perform mathematical operations like adding signals or integration. It is a true fundamental building block of electronics.
So there you have it. We've journeyed inside that little black box. We met the bouncer at the input, we felt the roar of the engine room, and we saw the forklifts deliver the final product. Everything working in perfect harmony. And that really just leaves us with one final exciting question. Now that you know how it works, what could you build with it?